On a hot sunny day, you decided to grab a glass of ice-cold water to quench your thirst. But as you were about to drink, you noticed some water droplets outside the glass. The culprit for this scenario? It's none other than condensation. When water vapor hits the cold surface, energy will be released and it will revert to a liquid form, and thus condenses.
But what happens if we cool this down to a temperature that is even colder than Antarctica? To answer this, let's dive into the subatomic level. I'm pretty sure that everybody knows the basic states of matter.
We have the solids, liquids, gases, and plasmas. Particles of every state possess a certain amount of energy. Among these four, plasmas have particles with the highest energy. Note that the energy of these particles correlates to the temperature at the macro level. If we rip off some energy from every state, we see the gradual decrease in motion of each particle as the matter undergoes some phase changes. If we take out more energy, the particles become cooler and cooler while continuously jiggling and wiggling and stretching, and then eventually merging into a single quantum entity in a form of a wave.
Alas, a new state of matter is formed. This new state is called the Bose-Einstein condensate.
According to quantum theory, subatomic particles can also be thought of as tiny wave packets. When we lower the temperature to almost absolute zero, the particles slowly behave like waves, which then begin to expand and overlap with each other. To get BECs, we'll need some free atoms of the same element to begin. We must then use lasers to hit them. The goal of the lasers here is to slow down the atoms. The temperature continues to drop as they slow down. A magnetic field is also employed to keep the atoms intact. Not all atoms will be slowed down by the laser cooling, and so the external magnetic field will be slowly decreased to let out the still highly energetic atoms.
Some elements wherein BECs have been achieved are rubidium, sodium, and lithium. BECs are utilized to make atom lasers, atomic clocks, and highly sensitive gravitational, rotational, and magnetic sensors.
To understand the big, we first need to examine the small. Thus, the study of BECs could potentially lead us to a wide portion of the universe that is yet to be discovered. So be observant, think critical, and stay curious.